All right, welcome back to part 4. Today, on the itinerary, we've got four things. We're going to express the heat diffusion equation from C1 as an algebraic equation, but this time we're going to be using the Crank-Nelson differencing. And then we'll also be using that Newman equation that we used in the last one to show the Crank-Nicolson difference scheme as a table regardless of what R you choose. So complete opposite of the last problem. This one, the R is going to be much more variable. And then we're going to simulate this time-dependent response of a 50 centimeter aluminum bar with a bunch of different specifications. And then we are going to discretize that bar and plot the simulated results in a 20-step time interval. And for the last thing, we're going to repeat D3 for a time step of 10 seconds. And R is going to be equal to 5. And we're going to show how the simulation, I'm reading that correctly, and show that while the simulation at early times, if inaccurate, the numerical resolution remains stable. So we're going to learn this as we go. I'm going to explain my work, I'm going to explain how we're doing, and we will learn together. So let's begin with our algebra. Now we're going to start with the same equation that we had up here, in which we have the derivative of time with respect to, I always get these mixed up. It's going to be temperature over time, and that is going to be equal to our alpha value times d second derivative of dx squared. Now we also want to be reminded that r in this case is going to be equal to alpha delta t over 2x squared. Now we got this in our last part of the problem, so we know what these means, and we are now going to start writing our equation as we move down this bar, in which this is going to be much longer, so it's going to take me a minute to write out. We have t times j n plus 1 minus t j n. This is all over delta t. And this is going to be equal to our alpha value, which again, we have right here. This alpha value, we're going to have a matrix similar to the one right here, but not the exact same. So we're going to have this part, and this is going to be t n plus 1 j plus 1 minus 2t n plus 1 j plus t n plus 1 j minus 1. Now this is all going to be over delta x squared. And then we actually have more in this, so we're going to do plus and then just kind of, we're going to have a variable here, but we're going to move it here. And the second variable is going to be t n j plus 1 plus 2t n j plus t, this is minus, j minus 1n. Now we are not done with this large equation. We are actually going to sub in this r value. We want this in terms of r, so we're going to take this actually and plug this into here, and that will be the next step. So you thought we were done with this complicated syntax, but we are actually not. So let's rewrite this all out again. Once we work through a lot of this matrix math and some of this stuff, we're going to have to write even more. So t j n plus 1 minus r. And again, this is after we subbed in, I'll draw this in red, this into here. That's the difference in this equation. So now we have r times t n plus 1 j plus 1 minus r times t n plus 1 j minus 1 equals t j n. So we're getting everything with the r term on the left, or sorry, we have things with r terms on the left and the right now, which obviously is not ideal, but we will get through that part. R t j plus 1n plus r j minus 1 minus 2r t j n. So we have this, and now we're going to combine some like terms into an equation that looks like this. Negative rt n plus 1 j plus 1 plus parentheses 1 plus 2r multiplied by t j n plus 1 minus r t n plus 1 j minus 1 is going to be equal to RT J plus minus 1 and plus 1. This is wrong. That's not that. Okay, I'm sorry. That is going to be equal to R times Tn J plus 1 plus 1 minus 2R times Tn J plus R Tn J minus 1. Now, this looks like a lot of places to make a mistake, a lot of places to mess up, which is true. But we are going to need this equation once we move into Google Colab. So don't forget this. I'll highlight this, and this is what happens when we use, I'll move this so you can see, this Crank-Nicholson equation to help us derive a new equation that will allow R to really be anything and not just minus less than 0.5. So next we need to make an equation using this, so I'm going to write this out, von Neumann. We need to use this to create an equation for all of our different temperature terms. And so that's going to start with Tn J plus 1 equals, like we did previously with these e's, it's going to be very similar, E IKX Tjn. Now I also have one where T is minus 1. And the difference in this is that this negative IKX times Tjn. Now we also need Tj plus 1 equals E negative alpha K T, this is squared, E I K times J plus 1 delta X. And then we also have Tj equals E now we have all four of these equations from von Neumann, and we are able to put these all together into one, which is the next part. So now let's put these all in like terms, and this will get us one step closer to showing why R can be really any value, thanks to Mr. von Neumann. Now, so once we put these all together, we have negative RE to the I K delta X times T n plus 1 J plus. I know this is a lot of algebra. This would be very easy to do wrong the first time. The only reason that I am not messing up is because I've done this, like we did it in class, and I did this beforehand before I started recording. That way I'd be able to work through it quicker. So as you see the algebra happening, just trust me, it is correct. I've double checked. And I'm just kind of going over it quickly because, again, this isn't necessarily, the algebra isn't the important part. You can ask, any of the AI programs, Chat, Gemini, whatever you want, and it'll do the algebra. The important part is understanding what's happening. And that is that we are taking these temperature equations using von Neumann, deriving it in a different way than the last part, and it's going to allow us to change that R value to something that is greater than 0.5, and it isn't going to punish us like it did in the last one by creating this volatile, volatile profile. And so here's the equation. When we simplify that down, we come to Tjn REIK delta X. So much algebra. It's disgusting. Especially when you can make little mistakes and it matters so differently. Okay, so here's our big equation right there, as you can see. And let's continue. So now, to prove that any value of R will never exceed 1, we are going to take the difference of Tjn plus 1 over Tjn. And what we're going to get is 1 minus 2R plus R times EIK delta X plus E negative IK delta X. Now actually it's super similar, so what I'm going to do here to save some time is take this, we're going to duplicate it. The only difference is that we're going to subtract this R this time. And what you're left with is E equals 1 minus 2R plus 2R cosine k delta x over 1 plus 2r minus 2r cosine k delta x. Now, from this, you are able to conclude never will exceed 1 for any value of r. So now we are able to actually take this and move into Colab. Let's do it. So as you can see, I've started in Colab, and as I like to say, I got our I have too many active sessions. Oops, let's get rid of some of these. Okay, let's cancel. I didn't know that was a thing. The more you know. Too many active sessions. Terminate existing session to continue. Manage sessions. I guess we're gonna have to close out all these. Let's refresh this and run. Manage sessions. What are we doing? Pause, I'm sorry, I gotta figure this out. Alright, figured that out. We terminated our other sessions and we are running, getting our chores done. Got the CHE5 in here. We also have our print options done. And we are gonna work through this just like the last one, step by step, and then learn this together. Alright, now, so this will go a little bit pretty quick because it is super similar to part C, in which we are going to set first our hour value, which is going to be equal to alpha times dt divided by 2 times dx, second derivative. Now, r will set equal to 0.5 like we did last time, but like we said, this doesn't matter nearly as much. And then now we're going to set some of our variables, which alpha is going to be equal to 1. Again, all these are from our specifications that were given in the problem statement. No explanation needed. So we have our variables here. Let's run this, make sure everything's running correctly. 4 green checks, that's the goal. So let's move to the next part. Just to let you guys know, when we ran this, r is equal to 0.05, and we will add a new line of code, and we want our iterations to be equal to 50 this time. We want our temperature to be equal to, again, this np.full, just like the last one, starting at 20. This is all the same as last time. T sub 0 is going to be equal to 40. Oh, typo. And then T negative 1 is going to be equal to 100. Again, these are all in Celsius. And now here things where they get a little bit different. We're going to add a new line of code. And this is AB is going to be equal to np.vstack. This is something that we learned in class that will allow us to plot this correctly. np.full n minus 2. If you can hear the motorcycles, I'm sorry. I live on a very busy road in Cincinnati. It is inevitable. It's the worst in the mornings when I want to sleep in. And I can't. Anyway, back to this. 1 plus 2 times r. So this is correct. Let's run all this, make sure everything is correct. All right, the check marks are good, and we were able to move into our IDX functions now. So now we want to begin the part of actually plotting this, and we will start with 20, and we'll look at our graph, and we will show how similar it is to the last problem, and then we'll actually switch that to 10 and redo it and talk through our graph. So that's a little bit of foreshadowing. So now we first have IDX is equal to np dot a range of n. Now we have big equals neighbors. Scatter x equals IDX t. I'm going to type this out and then kind of explain after. I've found that I make less typos when I'm not talking and typing. So we're going to be making a scatter plot here. X is going to be equal to IDX. Y is going to be the temperature, so we're able to analyze it. We want lines, and then we named it. So simple enough. Now we want a for loop here for n in range. Let's do 10,000. Make our colon, share everything in, and then we have AB, so let's just use B. B is going to equal to... Now these are the equations that we got from actually algebraic problem solving on our iPad. Times R, and then we want to multiply this by T. This will take a minute, so just bear with me. I like to go slow through this part, that the way I'm actually understanding what I'm typing and I make less mistakes. And that's our R value times the temperature, and this will be from value 0 to -2. And then we want to add the same thing, but instead this will be from 2 on. Now we want to do the same thing for B at 0. And this is going to be equal to R times T with 0. And then we also need to do B of -1. Sorry, this is going to be plus. Okay, so this first half is complete. We also need to do some T here from 1 to -1. And this is going to be equal to sp dot ln out dot solve underscore banded. Again, if you're unsure what these are all functions that we learned in class to allow us to code and plot these very funky and very specific situations. And then we have our if to end the for loop, n is 20%. And then finally we want to make a scatter plot, fig.add underscore scatter. And this is going to be our, that is very similar, so we're going to do this and then just get rid of what we want. We want this to be n plus 1. Okay, that looks correct, and then we make our fig. Let's see if it runs. Something's a little bit wonky here. We're supposed to have a graph similar to the last one, so let's figure out what's wrong. Okay, so genuinely really weird. I went through that, like I looked at that I think for like 20 minutes, and I could not, Gemini didn't have any ideas. I literally deleted it all, retyped the whole thing. Now we're working. Whatever. As you can see, we're very similar to the last one, where we have these temperatures that dip and then go back up, and then as the temperature gets closer to this top of the graph, they become more and more linear. But like I said in our homework, we want to repeat this, but a time step of 10, and we want R equal to 5, so that is the next step in this process. So as you can see, here's our edited graph. We switched this from 50 to 80, and we also switched this dt to 10 seconds. And as you can see, yeah, this red line outlier, get rid of that. This one's weird, get rid of that. So you can see this graph is still very stable, still following the same pattern that we need. And thanks to our, von Neumann equation and working through this algebraically, we were able to still complete this graph and showing that the temperature as you go down this pipe dips and then increases, but then also in some certain instances it is a very linear line. So thank you. This is the end of homework 2.